거기만 해결되면 시작할 수 있어서 제가 센터장한테 신호를 보내야 오래 걸리나요? 많이 오래 걸리나요? 그럴 것 같아요. 최대한 빨리 영어, 영어.
What? Ah, okay. So we are a little behind time, but let me do the opening. I'm Seo Gil-won from opening the 5th Korea-Russia Science Day event. So Honorable Academician Balega, Vice President of the Russian Academy of Sciences, Deputy Head Romanov of the Ministry of Science and Education of Russia, Chairman Kim Bok-chol of the National Research Council of Science and Technology in Korea, Deputy Chairman Kvartovkov for the Basic Research Foundation of Russia, Director General An Hwa-yong of the National Research Foundation of Korea, distinguished guest speakers and colleagues, I am extremely honored and happy to welcome all of you to the 5th Russia-Korea Science Day. Today we have gathered in the beautifully renovated President Hall of the Russian Academy of Sciences. Please allow me first to convey my sincere thanks to the Russian Academy of Sciences for providing such a wonderful venue and co-organizing today's event as events in previous years, together with the Russian Foundation of Basic Research. A special thanks to Olga Gluhovtsova and our staff at Korostech for organizing this event on the ground. On this other side, our Korean colleagues are participating online. Unfortunately, the very recent anti-COVID social distancing measures announced just days ago in Korea do not permit our colleagues to gather in one place, as we have here in Russia. Nevertheless, today we will learn about the latest achievements in the field of astronomy, space, from the top scientists of both countries. It is truly a privilege to be able to provide a bilateral science platform for those scientists so they could share their research results, exchange new ideas, and discuss future directions. This is especially true for mega sciences such as astronomy and space. Space does not have borders, as we know well. The study of space and astronomy should be open and a collective effort. Anyone interested should be able to take part and contribute. We are certainly here to display that spirit here today. Korostech embraces the same spirit of free scientific exchange and friendship. This year marks the Year of Science in Russia. We are already drawing to a close of it. Korostech is very proud to be a part of this event. There are so many things out there beyond our small world in space, the moon, the planets, other galaxies, black holes, wormholes, etc. There are also fundamental questions about how our universe came to be and how it is changing. The more we learn, of course, the more questions we run into. I hope that our scientific session today can help add to the wealth of knowledge that we already share about our universe. I would like to thank each participant for your part in advancing the horizons of astronomy and space science. Let me also personally thank you for contributing to development of friendly relations between our two countries. Lastly, I am sure the wonders of space have enchanted many, including myself, of course. As a child, I remember going to the countryside and looking up at the sky on a clear night. It still amazes me how many stars are in the sky. Now it amazes my children. We live in an incredible universe. Let us learn more about it and pass it on to our future generations. Thank you very much. Спасибо вам большое.
Dear participants of this meeting today, I will present the greeting talk of President of Russian Academy of Sciences, Alexander Sergeyev. He is invited because of the urgent problems of he's in the government now. So I'll read this slowly in Russian, just to give it time for interpretation for our Korean colleagues. Okay? Уважаемый господин Соги Лвон, уважаемые участники 5-го Российско-Корейского дня науки. Научное сотрудничество России и Республики Корея имеет давнюю историю. Важным событием российско-корейских отношений стало подписание 22 июня 2018 года меморандума о взаимопонимании
between the Russian Academy of Sciences, the National Council, Research Council for Science and Technologies of Korean Republic. The creation of the Russian Academy of Sciences with specific establishment of Russian is conducted with the support of KORESTEC, National Council of Research on Korea,
и технологиям Республики Корея. Совместно российско-корейские проекты реализуются в таких областях, как биология, химия и науки о материалах, математика, общественные науки, историко-филологические науки. И в этих проектах участвуют 42 института Российской Академии Наук. В результате совместных исследований получены новые результаты мирового уровня, которые публиковались в авторитетных научных журналах и были представлены на крупных международных форумах. Проведение Российско-Корейского дня науки стало нашей традицией. Ежегодные встречи ученых наших стран позволили вывести наше сотрудничество на новый уровень. Дни науки занимают центральное место в российско-корейских научных отношениях.
they help originate such interesting projects as
Передовые материалы, биотехнологии и другие. В нынешнем году актуальными темами научных сессий стали астрономия и космос, а также вакцинация от COVID-19. В России, как и во всем мире, известна своими достижениями Корейская астрономическая обсерватория Кимхэ, открытая в 2002 году в рамках реализации программы «Миллениум», разработанной в декабре 1998 года и направленной на изучение космоса и небесных тел. Тесное сотрудничество связывает специальную астрофизическую обсерваторию Российской Академии Наук, Астрокосмический центр Физического института Академии Наук и Корейский институт астрономии и космических наук КАСИ.
and it in its turn, the participation of ST, as you know, they're preparing in cooperation with our staff, will define further steps of developing astronomy interferometry for the decades to come. I would like to especially note the contribution of Russian-Korean Cooperation Center in Science and Technology, KOROSTEC, in cooperation of our two countries, and expanding areas of cooperation with scientific institutions, Russian Academy of Sciences and the Republic of Korea. Our joint work received support of the Korean Embassy in the Russian Federation. As a scientist, I'm confident that joint efforts of scientists from around the world will help us help us overcome new challenges we face. In 2024, the Russian Academy of Sciences will celebrate its 300 years. Due to this special date, we're planning to conduct multiple international events, and we do hope that Korean scientists will be actively involved in that important event for us. Thank you.
Является заместителем начальника Департамента государственной научной и научно-технической политики Министерства науки и высшего образования Российской Федерации Андрей Михайлович.
Mr. Romanov, thank you so much. Dear colleagues, on behalf of the Ministry of Science and Higher Education of the Russian Federation, I would like to welcome the organizers and participants of this scientific session, which is conducted today as part of the 5th Russian-Korean Day of Science. Undoubtedly, it's a significant event to share opinions, ideas, and experiences of the two countries to actively help scientific and technical dialogue and to deepen relations in the area of science and technology between Russia and the Republic of Korea. Even though difficult pandemic situation persists, bilateral cooperation in the area of science and higher education continues between Russian educational institutions and are involved with Korean institutions in such areas as telecom, medicine, space exploration, environmental science, and economy. In July to September, our institutions ran a tender for funding of joint projects for 2021-2022. 4 projects were selected. 2 of them are directly related to space exploration. Funding of each project on the Russian part will be 32 million rubles. Going forward, we can organize joint tenders on such areas as superconductors, quantum materials, millimeter and submillimeter radio astronomy. The LBI, Russian citizens are still interested as Korean citizens are interested to be educated in Russia. And currently in Russian educational institutions, over 400 South Korean students are being trained. Over 60 of them receive budget stipends from the Russian government. And special attention is given to technical education in such institutions as Moscow Aviation Institute, Bauman University, and Far Eastern Federal University. I would like to thank the organizers of today's event, and as well as KOROSTEC, the Russian Academy of Sciences, Russian Fund for Basic Research, and International Research Fund of Korea for their major contribution to the development of cooperation in the area of science between our two countries. And I wish you to have constructive dialogue, new ideas, and fruitful contacts and professional without another successes and for your plans to come through and stay healthy. Thank you.
Next greeting talk will be given by Kim Bok-chol, the chairman of National Research Council of Science and Technology of Republic Korea, NSTC. Please.
Hello, I am Bok-chol Kim, the chairman of the National Research Council of Science and Technology in Korea. I'm very pleased to be able to join you today at the 5th Korea-Russia Science Day. First, allow me to convey my sincere gratitude and regards to academician Alexander Mikhailovich Sergeyev, president of the Russian Academy of Sciences. Academician Yuri Yurevich Balega, vice president of the RAS, and academician Vladimir Pavlovich Chehonin, vice president of the RAS. Also, I would like to thank Deputy Chairman Vladimir Valentinovich Kvadrakov of the Russian Basic Research Foundation, and also Director General Hwa Yong-an of the National Research Foundation of Korea. Lastly, many thanks to Korean Russian Science and Technology Cooperation Center and the Director Gil Won-seo, Councilor Yoonok Choi for organizing this event from the Korean side. The Russian Academy of Sciences, established in 1724, has been the center of scientific thought and knowledge that influenced not only Russia, but also the whole world. RAS is well acknowledged for its profound contribution to many fields of science, including physics, medicine, mathematics, biology, and geology. Many Nobel laureates are associated with the RAS, such as Ivan Pavlov, Ralph Landau, Alexander Prokhorov, Pyotr Kapitsa, and many more. The Russian Academy of Sciences also played a pioneering role in ushering in the space age and space exploration. The National Research Council of Science and Technology support and manages 25 government-funded research institutes, we called GRIs, in the field of science and technology in Korea. We adjust and align the functions of GRIs and support cooperative research between GRIs to maximize research performance. GRIs have been collaborating with Russian researchers in various areas. In the past, the Russian Science Soul Center of the Korea Electrotechnology Research Institute, together with Russian researchers, developed femtosecond laser. And recently, the Korea Railroad Research Institute has been conducting a joint research with Russian researchers in new railroad technology. This year, in August, the Korea Railroad Research Institute also participated in ProMotion Expo. In June 2018, NST signed a Memorandum of Understanding with the Russian Academy of Sciences. However, in less than 2 years, the world has been changed enormously due to pandemic. Our plans of collaboration with the RAS naturally has also been affected. Nevertheless, NST is continued to renew collaboration and interaction between two organizations. The Korea-Russia Science Day was first inaugurated in 2017, aiming to promote exchange between the scientific communities of both countries. In the last 4 years, it has become a solid platform for scientific exchange in important fields, such as artificial intelligence, aerospace sciences, advanced materials, biotechnology, and etc. This year, the 5th Korea-Russia Science Day is dedicated to astronomy and space and vaccinations, which are very timely and urgent issues. I believe many meaningful discussions will be held, and I hope many ideas for cooperation will be exchanged during this year's sessions. In closing, I'd like to see you all the next Korea-Russia Science Day, hopefully in Korea. Thank you very much.
Bok Chol Kim. And now the word for greeting is given to Vladimir Valentinovich Kvardakov, corresponding member of Russian Academy of Sciences, Vice Chairman of Russian Foundation for Basic Research. Please, Vladimir Valentinovich.
Большое спасибо. Уважаемые корейские и российские коллеги, уважаемые члены президиума, уважаемые дамы и господа, позвольте мне приветствовать вас от имени Российского фонда фундаментальных исследований, председателя совета нашего фонда, академика Владислава Яковлевича Панченко и себя лично, и поздравить вас с 5-м Российско-корейским днем науки. Российский фонд фундаментальных исследований – первая из отечественных финансирующих науку организаций, которая стала оказывать грантовую поддержку фундаментальных исследований как внутри России, так и в рамках международного сотрудничества. Нашему фонду через несколько месяцев исполняется 30 лет. А российско-корейским дипломатическим отношениям в этом году исполнилось 31 год. Сопоставимая цифра. Российский фонд фундаментальных исследований имеет в Корее надежного партнера – Национальный исследовательский фонд Республики Корея. И ровно 10 лет назад, в 2011 году, был объявлен первый совместный конкурс по поддержке фундаментальных исследований, двухсторонний конкурс. С этих пор совместные конкурсы стали регулярными, проводились каждые 2 года. Все было 5 таких конкурсов. Последний был проведен в прошлом году. Такие конкурсы пользовались огромным успехом. За все время было собрано 230 заявок, поддержано 31 проект на общую сумму около 100 миллионов рублей. Сотрудничество наших фондов распространяется в том числе и на область научной дипломатии. Именно в партнерстве с Национальным исследовательским фондом Кореи наш фонд провел в Москве в 2018 году заседание Глобального исследовательского совета, который объединяет все ведущие фонды, финансирующие науку, все фонды мира. От России в этом совете представлен только Российский фонд фундаментальных исследований. Теперь перед Российским фондом фундаментальных исследований и Национальным исследовательским фондом Республики Корея стоит задача продления соглашения о сотрудничестве, где прошло 10 лет. И мы активно думаем о возможных рамках продолжения этого сотрудничества с учетом тех реорганизационных процессов, которые, к сожалению, коснулись и нашего фонда. Будущее РФФРИ официально пока не определено, но мы надеемся, что оно будет светлым, и это сотрудничество окажется на еще более высоком уровне. Отмечу, что следующий год объявлен Организацией Объединенных Наций как годом фундаментальной науки. И этот год трудно представить без Российского фонда фундаментальных исследований и без международного сотрудничества. А это сотрудничество со стороны России трудно представить без активного сотрудничества с Кореей. Тематика настоящего дня – астрономия и космос. Примечательно, что это событие происходит сразу после такого важного астрономического события, как День зимнего солнцестояния. С сегодняшнего дня день начал пребывать, а тьма отступать. Это хороший знак для нашего общего дела. У нас говорят: да будет свет. Это слова не только из Библии, но и из науки. Кстати, недалеко от Кореи, на острове Русский, начинает сооружаться один из мощнейших источников синхротронного света. И этот источник может быть также точкой сотрудничества наших государств. Позвольте поблагодарить наших корейских коллег за плодотворное сотрудничество и пожелать всем участникам сегодняшнего форума успехов и отличного здоровья. Большое спасибо.
Thank you very much. The word for greeting is given to An Hwa-young, General Director on International Relations of the National Research Foundation of Korea. Please.
Здравствуйте, очень приятно. Good morning, ladies and gentlemen. I am Hwa Yong-an, Director General of International Affairs of the National Research Foundation of Korea. Let me begin by expressing my gratitude to President Alexander Mikhailovich of the Russian Academy of Sciences and Chairman Vladislav Yakovlevich of the Russian Foundation for Basic Research for the efforts to co-organize this event despite the difficulties caused by COVID-19. In addition, I'd like to extend my sincere appreciation to Vice President Yuri Yurievich and Vice President Vladimir Pavlovich and Deputy Chairman Vladimir Valentinovich for taking the time to be here with us today. The coronavirus pandemic has brought significant changes to the world and our way of lives. Now, you are also facing great challenges in terms of international cooperation in the field of science and technology, including the exchange of researchers between countries. It is very encouraging that KORSTEC, Russian Academy of Sciences, and Russian Foundation for Basic Research have been cooperating to hold regular Science Day events under these difficult conditions. Passing through this pandemic, the countries in the world share a common goal of fighting off infections. In addition, all of us have realized that the current goal cannot be solved just one country's efforts. Russia has developed 4 vaccines, including the famous Sputnik V, Epivac Corona, Covivac, and the Sputnik Light vaccine, and also is developing various vaccines such as in the nasal and fermented forms So far, Korea has relied on overseas vaccines, but also has been making efforts to develop its own vaccines. As a result, vaccines of 7 companies are currently undergoing clinical trials in Korea. I hope that this forum will be a good opportunity to share knowledge and experiences in the field of vaccines and establish a cooperative platform to cope with the current COVID-19 and the possible diseases in the future as well. Another topic, space is the area where the cooperation between the 2 countries is very promising. No one can deny that Russia is one of the most advanced countries in the field of space. Although Korea started many steps behind, it has tried to lay the foundation for space technology and narrow the technological gap with the countries standing ahead. In this process, the 2 countries have valuable experiences of cooperation. Korea's first space launch vehicle, NATO, equipped with Russian-made engines, is a good example of cooperation in this area. This became a valuable experience for Korea's first self-developed space rocket, Nuri. The recent launch of Nuri has significantly increased interest in the space area in Korea. It's very meaningful that you have prioritized the cooperation in astronomical observation and space exploration, which are the basic fields among the various fields of space sciences. I also look forward to cooperation in other fields of space sciences in the future. Although you are facing each other only through the screen, I am very confident that this forum will contribute to lay the cornerstone of more active communication and further cooperation between the scientists. In conclusion, I'd like to deliver thank you to Director Seo Gil-won and the staffs at KORESTEC for their hard work in Moscow. Finally, I'd like to congratulate everyone involved on the successful hosting of the 5th Korea-Russia Science Day event. I wish you health and great success. Thank you all so much. Большое спасибо.
Much, Mr. An Hwa-young. And this was the final greeting talk today. So we have to decide now. So following our program, we have a coffee break, but because slightly late. So what I recommend, just let's begin to our working program, and then maybe a little bit later, half an hour from now, we'll make a break and then make a coffee break, okay? Because to be more or less in a schedule. So, dear participants of our meeting, I'm very glad that this meeting is devoted to astronomy. Astronomy is my professional interest also. So, of course, this is extremely important for me too personally. As you probably agree, astronomy is the science #1 in the world. This is a king science. Why? Because it integrates the fundamental achievements of the basic sciences And it gives us the understanding of what we are in this world, in this universe. We are microscopic particle in the world from one side, and from another side, it includes the top achievements of our technologies all over the world. These are top achievements in mechanics, in optics, in electronics, in software, different things, in big data and artificial intelligence. So everything. Modern instrumentation for astronomy, they are starting from very short wavelengths and starting from gravitational waves and finishing the long wavelengths in radio astronomy. So all this spectrum of electromagnetic waves and gravitational waves gives us all the information about the world where we live now. So it's very important to exchange the knowledges in this field and achievements during these Russian-Korean science days. And I'm sure that we will listen today for very interesting talks. And just to confirm that the astronomy is a science #1, just please take into account the Nobel Prize winners during last period. These were just maybe I forgot something, but dark matter and dark energy, extrasolar planets, exoplanets, gravitational waves, black holes recently. So all these Nobel Prizes in physics were devoted to astronomical subjects. So let's start our working program today. And first, I would like to give the word to Professor Eson Chun. This is Seoul National University about lunar problems. So please, Dr. Eson Chun.
Do you see my presentation?
Yes, yes, we see it. Okay.
Okay, thank you. Good afternoon. On behalf of every lab team, it is my great honor to present scientific applications of LV-RAD. I am Song Jun-ye from Seoul National University. LV-RAD stands for Lunar Vehicle Radiation Dosimeter. The LV-RAD team consists of scientists and engineers from Korea Astronomy and Space Science Institute, Seoul National University, Gyeongbuk National University, and Cheongju University. Here is the motive. US NASA plans crewed lunar lander missions in 2024 called Artemis Project. Korea also planned to launch a lunar orbiter and landers in 2020 and 2030, respectively. LV-RAD is developing to measure radiation environment on the lunar surface and to evaluate biological effect on human beings. Due to a very scant presence of gases surrounding the moon, the lunar surface is exposed by all kinds of radiation, such as galactic cosmic rays, solar energetic particles, albedo neutrons, and gamma rays, and so on. As I mentioned, primary object of LV-RAD is to measure radiation environment on the lunar surface and to evaluate the biological effect of human beings in terms of observed dose, dose equivalent, and ambient dose. The secondary object of LV-RAD is to analyze lunar space radioactive substance by gamma-ray spectroscope and to find out the evidence of water ice by measuring thermal and epithermal neutrons. To do that, four types of radiation detector has been developing now since 2020. Some of them already have heritages from the ISS CREAM missions and the NASA balloon programs. Actually, LV-RAD consists of three modules: particle dosimeter and spectrometer, and tissue equivalent dosimeter is one module in first, and then fast neutron spectrometer is the second module. Thermal and epithermal neutron spectrometer is the third module. This is the work breakdown structure. Overall, the Seoul National University is in charge of science and assessment. KESI is a core institute of system development and integrations. Gyeongbuk National University and Cheongju University play a key roles of developing various sensors for neutron spectrometer and particle dosimeter and spectrometer, such as silicon sensors, lanthanum chloride crystals, steel bands, lithium iodine silver sensors, and dosimetry algorithms. In addition, we have a consultant from Space Environment Group in NASA JPL. From now on, I will briefly introduce each of LV-RAD components. As I mentioned earlier, LV-RAD is composed of three modules: lunar radiation dosimeter and spectrometer, and fast neutron spectrometer and thermal epithermal neutron spectrometer. First, in the lunar radiation dosimeter and spectrometer module, particle dosimeter and spectrometer can measure proton spectrums from 1 to 500 MeV by using stacked silicon, sodium iodide, and silicon sensors. And tissue equivalent dosimeter mimics 2-micron tissues to measure linear energy transfer spectrums, which is very essential information to evaluate biological effect of radiation. By using plastic detector for anti-coincident, TED can distinguish each contribution from charged particles and neutrons. Fast neutron spectrometer can detect fast neutron spectrums from galactic cosmic ray albedos on the lunar space through the nuclear reactions with lanthanum chloride and steel bands. Signals from neutron and gammas can be separated using pulse shape discrimination method, and then separated neutron pulsate spectrum can be converted into neutron spectrums using unfolding method, which is under development. In addition, fast neutron spectrometer can measure gamma-ray spectrums emitted from lunar surface radioisotopes. From this information, one can estimate lunar surface compositions. Finally, thermal and epithermal neutron spectrometer is developed to seek out the evidence of water ice existence on the lunar surface. It consists of two sets of lithium iodine silver sensors, one set with 0.5 millimeter cadmium filters and the other without it, which can provide ratio of thermal to epithermal neutrons. A higher ratios of thermal to epithermal neutrons indicate high hydrogen abundance, most likely on the South Pole area. This is the end of my presentation. Truly, we would like to have a collaboration with Russian scientists, Russian space scientists, especially in the area of space radiation environment. Thank you for your attention.
Thank you very much, Professor Son Jun E. And next talk is will be given by Gennady Valyavin. He is a director of the Special Astrophysical Observatory in Russia, Russian Academy of Sciences, the largest observatory in our country.
Вот здесь.
No button here. Okay. So I hear myself. No, everything's okay. Thank you very much. Just a moment. Sorry. Pardon. Excuse me, could you please start it again? Okay, thank you very much. Kamsahamnida. First of all, thank you very much. And I would like to thank the organizing committee and especially Yuri Paleger for providing me with an opportunity to give an oral talk at this nice conference. Thank you a lot. So my talk is about the Joint Optical and Radio Astronomy project of the Special Astrophysical Observatory and the Korea Astronomy and Korea Astronomy and Space Science Institute. But before that, I would like to say a couple of special words addressed to our Korean friends. Probably some of you knows that I have an experience working in Korea between 2003 and 2008 in Korea Astronomy and Space Science Institute, and this experience made a very strong influence to my personal life. At least my son started his life there. You see them, and this is my family. And this is our habitable zone in Korea, very near to the Yeoncheon city, close to such a remarkable place like Bulguksa Temple and Katpao Temple. And I have an opportunity to thank again our Korean friends for such experience. Thank you very much. So I would say that since that time, Korea is very deeply in my heart. So and now is my talk. Currently, we have two joint projects between the optical division of the Special Astrophysical Observatory and the CASI, and we also have plans to extend our collaboration to radio. Nowadays, we've been working for 10, maybe 15 years in a very close collaboration to the team of Dr. Ino Han, the former director of the CASI, and another guys in his company is the Bjorn Cholvi and Kanbin Kim. So very nice guys and our very good friends. So, and now I would like to tell a little bit more about our observatory to our Korean friends. You probably know our observatory is known by its 6-meter telescope, which was the largest one until 1993. Then after that time, the two 10-meter Keck telescope in the United States started to operate in Hawaii, and then several more 8-meter European telescopes, and Chinese telescopes started operation in Chile and Hawaii too, as well. So, and we are now, of course, it's not the largest one, but nevertheless, we are still significant institute, astrophysical institute, which operates in our country. It is located in the North Caucasus, Nizhny Arkhis village, and the 6-meter telescope is located at the height of 2,070 meters above the sea level. Then, except the 6-meter telescope, we have also a group of telescopes with small apertures, small objects with small lenses. It's a 1 meter, 0.6, 0.5 meter telescope, and so on. Then we have also a big radio telescope, Proton 600. And now you see the 6-meter telescope as it is right now. It is really huge. The length from the prime faucet to the main mirror is about 24 meters. So it is really huge, as you can see. You can imagine how big it is, the dome there and everything inside. So, the instrument is not only big, it is in very good conditions and completely remotely controlled. In principle, I'm able to operate it right now by using internet. It is, of course, it is prohibited administratively, but nevertheless, such possibility exists. So, and all the instrumentation located in these two balconies and the prime focus tube as well. Then the instrument has a complete range of modern astronomical instrumentation for observation near ultraviolet, visible, and near infrared wavelength region in these 4 regimes. You are probably not so familiar, just I count them because many astronomers them too. So this is the high, moderate, and low resolution regime, the broadband photometry and photopolarimetry. Then it is diffraction limited angular resolution imaging. This is, by the way, this responsibility of Yuri Yurich Balega. He still works there, he's active scientist. I very respect this activity. Then, and it has also a high temporal 10 and minus power 6 second resolution, 1 million frames per 1 second. Then such instruments we have. And we have also a smaller group of telescopes. This 1-meter telescope and astronomical instrumentation contains all the necessary modern techniques, spectroscopic techniques, photometry, and so on and so on. And the group of small telescopes, that is apertures from 0.5 to 0.6 meters, several ones. This is purely photometric instrument, which their business is to search for exoplanets. Now, the SAORAS is active in all areas of ground-based observational astrophysics, astrogalactics, stellar, and some other asteroids, comets, and so on. In the field of galaxy studies, the most significant this is my personal point, and I very like this kind of studies. This is a mapping of spatial, chemical, and velocity structures of distant galaxies by methods of panoramic Fabry period spectroscopy. Here on the left panel, you see the image reconstructed with the aid of 1-meter telescope. The technique, as you see, is quite advanced and very well organized. Then the long-slit spectroscopy and photometry of distant galaxies, which studies big relativistic objects, black holes, white dwarfs, and so on and so on. Here you see an example of the study of active galaxies. The left panel corresponds to its direct image, and the right panel is the spectrum of the galaxy, and these vertical lines corresponds that there is a hot ionized gas around this galaxy. So the oxygen, helium, and so on and so on. Then we also take participation in spacecraft missions like SRG and Rosita surveys. The South supports both these projects nowadays, and we are now preparing to participate in the PLATO European project, which is aimed for study of exoplanets, and our Russian Spectre UV. Then the SAORAS is active in stellar astrophysics as well. It has a very long, strong tradition of multi-instrumental studies like cataclysmic stars, relativistic objects, black holes, stellar magnetism, and from recently studies of exoplanets. In particular, in studies of stellar magnetism, very recently we have carried out the simultaneous mapping of a white dwarf. White dwarf, this is degenerate star, which is the final stage of the stellar evolution. And we first reconstructed the distribution of magnetic fields of the surface simultaneously with the distribution of its temperature and found their exact correlation. This result was published in Nature, and this result was obtained after a very long, about 10 years observation in collaboration with our Korean colleagues from the CASI by Inu Han's group. Then, and starting from that time, the study of stellar magnetism becomes the first joint project of the Special Astrophysical Observatory in the CASI, in particular the Bonkinson Observatory, which is the one in the CASI. You see this observatory at the left panel. This is the observatory, Bonkinson Observatory. I've worked there for 4 years. And the right panel is their main instrument, 2-meter telescope equipped with an excellent, very good spectrograph, which we are still working and exploring together. And the second joint point is SAORAS and CASI is spectroscopic study of exoplanets. I don't mention any of the results because we have just recently started this project. I just mentioned that we carry out these spectral studies by using the 6-meter telescope in the right panel and the 2-meter telescope of the Bonkinson Observatory. Such situation, and my time is over, but just a couple of words about our radio. I already mentioned above that we have also another one giant radio telescope, which is, it looks like you see it here. It has the huge circular antenna with diameter of about 600 meters, with a number of antennas element about 900. Each of these panels, each of these elements is remotely controlled with very good conditions, of course, and it is actively worked nowadays on the modern level. Of course, this instrument is not so advanced like, for example, Arecibo, which is unfortunately very recently finished his life. But there are nevertheless, there are several advantages in this ring-like construction of our telescope. For example, there are possibilities to observe in different sectors of the Ratan 600 antenna with complete range of modern astronomical instrumentation for multi-channel observation in 1 to 20 centimeter wavelength range. So, and finally, having this solid and strong experience in centimeter astronomy, SAORAS is considering expanding this range to millimeters. We are planning this project through participation in a large collaboration of Russian astronomical institutes under the ideological leadership of the Russian Academy of Science and the Lebedev Institute as a PI, and probably if our Korean colleagues will be interested in this kind of collaboration, is the CASI as well. In particular, it could be a 15-millimeter wave dish radio antenna working in the single dish mode, as well as a part of the existing interferometers like Even Horizon Telescope, PHT, or as a part of the future projects like Millimetron and SUFA. So in our business here, we would like to provide, if this project will be supported, so if we get the financial support from Russian Ministry of Science. So we will provide this, we are ready to provide this project with our infrastructure. So they have all the necessary scientific infrastructure. They could put this instrument somewhere here. There's the slope of the Pastukhov Mountains, which is the place of location of the 6-meter telescope. So, and provide this very experienced staff. So, but, and from now I'm leaving this point for the more experienced company, for the next speaker, Likhachov Sergei Fedorovich, who is probably will be behind this project. Thank you very much.
Thank you very much, Dr. Valyavin. We do not ask questions now. Probably we'll leave this time for discussion in the end, okay? And now, as I promised, let's make a short coffee break for saying we're slightly out of time. So let's for 15 minutes, 1-5, not 50, but 1-5, 15 minutes coffee break. And the next speaker will be Dr. Chon Boon Seop. I don't know which correctly is maybe more correct. Boon Seop Chon. What is better?
Yeah, perfect.
Okay, so next speaker is our Korean colleague from Institute of Astronomy. So now we'll make a break for 15 minutes. So we start at 11:27.
Eun-seo. He from Korea Astronomy and Space Science Institute. He will talk about infrared space missions in Korea and future prospects with the Millimetron.
Okay, my name is Eun-seo Jung from Kashi. Thank you for giving me the opportunity to present the Korean infrared space mission and possible international collaboration between Russia and Korea with the Millimetron space.
Hello, Eun-seo? Hello? Hello, can you hear me? We lost Eun-seo Jung's connection, so I just quickly talk with him and by phone, and then he will soon reconnect this. Will soon be appeared here. So just wait for a moment. I'm sorry that Eun-seo Jung is trying. Yes, he is now online. And Eun-seo, can you share your screen? And you can turn off your video if your connection is unstable.
Yeah. Can you see my screen?
Yes, I can see you. Yes, you can start.
Okay. Okay. I start my talk. Okay. Okay. Maybe I stop my video. Okay. Can you see my screen?
Yes, we can see.
We see everything. Start it.
Okay. Yeah. Yeah. Thank you for giving me the opportunity to present the Korean infrared space mission and possible international collaboration between the Russia and Korea with the Millimetron space observatory. As you know, Kashi is involved in the many ground space projects. In this talk, I will present the topics on the infrared space mission for the astronomical research. This picture shows the cosmic history from the Big Bang to the current universe. Our main research topics with the infrared space mission are to trace the cosmic evolution of the first galaxy or stars. To reveal the cosmic star formation history, we have to understand the evolutionary stage of the individual galaxies. For example, from the star-forming galaxy and also merging one, and some starburst mode to the red and dead galaxy. For that purpose, the dust obscured the star formation history was studied through the many previous space missions. Although the peak of the star formation rate density is around the redshift of the 2 and 4, but we could not fully understand the dust obscured star formation history. In addition, the infrared excess emission are detected in the near and far infrared region, which were not explained through the current data set. Therefore, we have to focus on the infrared excess emission, which were located in the near infrared as well as the far infrared region. So the origin of the infrared excess emission are thought to be originated from the first stars and galaxies, or merging signature of the stars around the galaxy, or unresolved faint galaxy population. So we called those components is the extragalactic background. So we have to understand the origin of the extragalactic background, right? So here are a brief introduction of the Korean infrared space mission. First one is the MIRIS, was the wide infrared imager in INH band and partial alpha band as well. For survey of the near-infrared sky, it has performed the first galactic plane survey in partial alpha emission line, like this. And also from this survey, we also achieved the this mission launched in the 2018. It was some near-infrared imaging spectrum with from the 0.9 to 0.5 micron. Also, it can be obtained simultaneously imaging as well as the spectroscopy. Two missions was the optimize the diffuse object, since owing to the small aperture of the 8 or 15 centimeter something. Also, regarding some international collaboration, there was some Akari mission. Akari also, some Japanese mission. It will perform the second all sky far infrared survey. After that, recently, SPEARX is approved as the NASA MIDEX mission. So Kashi is some unique international partner for this mission. So I'm leading some Korean consortium of this SPEARX project. Also, it is the first all sky infrared spectral survey. Some spectral resolution from this range with the spatial resolution around some 6 arcsecond. So as I mentioned, SPEARX is some NASA MIDEX mission. It will be launched in the 2024. So Kashi will participate in the hardware development, also data direction, as well as some science. Major scientific objective of the SPEARX is it will improve the limit of the non-Gaussianity, some FNL, by the factor of the 10 through the advantage of the all sky survey. Also, SPEARX will measure the extragalactic background light fluctuation spectrum from their spectroscopic capability. So as you see in this figure, there are around 100 spectral channels. So from this information, it will reserve the origin of the EBL component. And also, SPEARX will survey the high quality ice sources in the galactic plane region. So from this, SPEARX will achieve many types of source like this. Also, there are some cosmological deep field in the North security pole and South security pole region for the extragalactic study. Akari also observed the 2 ecliptic pole region. So as you know, those regions will be observed by the Euclid and also SPEARX as well, and also Erosita. as I know, some Rosita was partly participated by the Russia. So moreover, some SPIRAC will cover those regions up to the 100 scale degree area in the deep spectral photometric capability. Okay, as I mentioned, our research interest is the study of the dusty star-forming galaxies, which might be contribute to the ISA galaxy background rise. There are lots of some infrared luminous galaxies, so-called star-forming galaxy, starburst, ultra-luminous infrared galaxy, also sub-millimeter galaxy, and dust obscure galaxy, and so on. From the previous our Akari Deep Field North and South survey, we already achieved more than 10,000 galaxies in the survey area. For example, some Herschel survey, it will acquire some more than 10 to the 6 galaxies. However, from there was some imaging survey, but there's some lack of some spectroscopy information, maybe below the 10%. From the those target will be investigated from the next infrared submillimeter project, such as James Webb Space Telescope, also SPIRAC, and SEACAT, as well as the Millimetron. So Millimetron is the powerful space observatory in the far infrared and sub-millimeter regime. So it will be unique far infrared space mission in the space 2030. It will realize the 10-meter class cooled telescope below the 10 Kelvin. For example, so some JWST, some 6.5 meter aperture. In the single dish mode, it will observe the far infrared sub-millimeter region. Also, it will make some confusion limited observation in the imaging and spectroscopy mode. So this one picture shows some example of some confusion. So you can see that some 1 meter telescope and 3 meter telescope. So with the 3 meter telescope, the diffused dusty structure can be resolved some accurately. Also, many point sources can be resolved some individual point source. Also, when you zoom up this faint region, so 3 meter telescope is on quite some higher spatial resolution. Like this, 10 meter class millimetron can be make some confusion limited observation is realized. So I showed several scientific results from the previous research. So we found the sub-degree scale of the spatial fluctuation of some EBL in the near infrared region, like this, which is some peak around the 1 degree scale. After that, it decreases abruptly. SPIRAC will resolve the origin of this EBL component, whether this is from the epoch of the reionization or the more recent universe. Even in the far infrared regime, we also found the EBL component, which will observe the clustering feature. Judging from the spectral feature, we conclude that this is the originated much redder color of the galaxy. For example, ULOG or some dust obscured galaxy and so on. So this study is also possible with the Millimetron. So to understand the physical properties of those galaxies, the follow-up observation are important. So we have used the sub-millimeter observation in ground, for example, some JCMT and SCUBA-2. Owing to the better beam of the SCUBA-2 of the 13 beam, so we can deblend the source from the Herschel source like this, this one. And also through the optical near-infrared spectroscopic follow-up, we have traced the cosmic star formation history up to the register of the 2. this result also can confirm that red galaxy can be contributed in the higher to the star formation density in the higher redshift range, like this. So during the follow-up observation, so we have found the interesting object, so-called the heavily obscured galaxy in the high redshift range, which was selected from the extreme red color with the optical and mid-infrared. So those population is expected to have some very short time phase like the starburst, like this. So it can be contributed to the evolution phase from the merger supermassive black hole to the red dead quasar. So we have some studies on those types of galaxy. So from the preliminary survey, we have some measured the black hole mass and stellar mass. So this one is our result. As you see in this result, most of some black hole mass is more than 10 to the 9 solar mass. Also, those type is follow the local relationship, like the hyperluminous hot dog, but some sausages have some in the peculiar mass range. So there are some lots of some questions for this one. Why there is some so high luminosity AGN? It's maybe from the major merger or some ranging case. Also, we cannot explain the high obscuration. So we couldn't find some O3 outflow or some H-beta emission. Also, some sausage is in the extreme the stellar mass. And also mostly it has some high Eddington ratio. So there are so many of lots of questions for this source. Maybe follow spectroscopy follow-up from the millimetron can reveal the this many questions. And also we are also expecting synergy with the ground-based telescope. So there are lots of new catalog from SPIR-X and as well as millimetron. So we can access the foreign facility, for example, some Gemini and MMT, and also as for the some EAO partner, we can have some access on the JCMT and ALMA as well. Also, we are going to participate in the future facility, for example, the Giant Marginal Telescope, also LST, and so on. So it can be make some synergy in the many science cases. For example, some galaxy assembly and evolution, and also fundamental physics of the physics of first star and galaxy, and so on. Okay, we'll make some summary. We have some experience in the development of the infrared space instrument with the small space mission. Also, recently we have some participate in the NASA Mid-X mission SPIR-X. So from this survey, we can acquire some many new catalog. Maybe from this some interesting source can be traced by the millimetron. So study of some cosmological deep field give us some many information on the physical properties of the infrared bright galaxies in the distant universe. So we are expecting also synergy with the ground-based telescope for exploring the high universe. So for that point, millimetron is also good make some synergy with some facility. Okay, thank you.
Thank you.
Thank you very much, Dr. Woon Seop Chon. Now we continue our talks, and next speaker is Anatoly Alexeyevich Petrukovich, corresponding member of Russian Academy of Science and director of Space Research Institution. Please, Anatoly Alexeyevich is online with us.
Добрый день, уважаемые коллеги. Вы меня можете слышать? Покажите, пожалуйста, презентацию.
Слышим, слышим.
Я бы хотел сделать краткий обзор российской научной космической программы. Практически все проекты этой программы осуществляются в широком международном сотрудничестве. Я думаю, после этой презентации могут возникнуть какие-то новые идеи о взаимодействии российских и корейских ученых. И я бы хотел здесь осветить кратко те проекты, которые сейчас находятся уже в полете в космосе, те ближайшие запуски, которые нас ждут в ближайший год-два, и наши планы на 5-10 лет вперед. Следующий слайд, пожалуйста. Что у нас сейчас находится в космосе? Прежде всего, это целый флот космических аппаратов Европейского космического агентства, НАСА и Японского космического агентства, которые имеют на борту российские приборы. Приборы, которые изготовлены в рамках российской космической программы, но установлены на иностранных аппаратах. Прежде всего, с 1994 года уже почти 30 лет работает гамма-детектор на американском космическом аппарате ВИНД. Там гамма-детектор Конус, сделанный в Санкт-Петербурге, где я сейчас нахожусь. Далее. Да, вот мне тут, прошу прощения, коллеги подсказывают. Верните, пожалуйста, предыдущий слайд. Мне коллеги подсказывают, что я должен говорить по-английски или по-русски нормально.
Можно говорить по-русски, только не так быстро, нам переводят нашим.
Хорошо, я буду продолжать по-русски. Далее, с 2000 года было запущено почти 10 российских приборов планетного назначения для исследования Луны, Марса, Венеры. И сейчас, например, крайний запуск на борту японского проекта Бэппи Коломбо работают 3 прибора с существенной российской частью на борту. Это Фебус, МГНС. Фебус это гамма-детектор, полностью сделанный в ИМСАСе. В Фебусе и ИМСАСе Институт космических исследований выполнял существенную часть прибора. Следующий, пожалуйста. Еще один очень важный международный проект – это российско-европейский проект «Экзомарс». В 2016 году был запущен орбитальный аппарат «Экзомарс», это европейский спутник, и 2 из 4 научных приборов на борту, то есть половина всех научных задач решается 2 российскими приборами, которые успешно уже практически 5 лет работают на орбите Марса. Второй существенный компонент этого проекта – это совместная система дальней космической связи. Впервые в рамках этого проекта российские антенны дальней космической связи были полностью синхронизированы и адаптированы для приема сигналов с европейского спутника и для управления европейским спутником, то есть для работы по международным стандартам. И это очень серьезный задел. Это будет использоваться эта возможность использования российских антенн будет востребована, безусловно, во всех будущих международных проектах. Сейчас более 50% информации проекта «Экзомарс» передается через российские антенны. А «Экзомарс» – это не только научный спутник, это еще и ретранслятор. То есть практически 50% ретранслятор тех научных аппаратов, которые работают на поверхности Марса. То есть существенная часть всей научной информации с Марса сейчас идет через российские станции связи. Следующий, пожалуйста. Второй и самый главный российский проект, находящийся сейчас в космосе, это астрофизическая рентгеновская обсерватория «Спектр РГ». Здесь тоже это проект с существенным международным участием. У нас есть на ней установлены 2 рентгеновских телескопа. Телескоп мягкого рентгена – это немецкий эксперимент, а телескоп жесткого рентгена – это российский эксперимент. Обсерватория уже отрабатывает свой 3-й год в космосе, и более 3 сканов неба уже составлено. Как раз сейчас, в эти дни, в Институте космических исследований идет специальная конференция, посвященная рентгеновской астрономии, где представляются последние результаты этого проекта, и все желающие могут подключиться к ней онлайн. Далее, что нас ждет в ближайший год? Он обещает быть богатым, следующий слайд, пожалуйста, на новые проекты. Прежде всего, мы ждем запуска второго этапа проекта «Экзомарс», посадочного аппарата с ровером, который уже в данный момент собран, находится в Европе и в ближайшие месяцы должен быть переправлен на Байконур и запущен в космос. Это совершенно уникальный проект международного взаимодействия по глубине интеграции. Российская ответственность – это существенная часть посадочной платформы, это научные приборы посадочной платформы и ровера. Европейская часть – это электроника посадочной платформы, парашют, научной аппаратуры на платформе и большая часть научной аппаратуры ровера. Это очень сложный проект не только в научном, но и в технологическом смысле, потому что подразумевает сейчас, что фактически часть интеграции российского космического оборудования делается на европейских космических предприятиях. Это практически совершенно уникальный случай, и тоже это задел для будущего очень эффективного сотрудничества в гораздо более сложных проектах. Следующий, пожалуйста. Еще один проект, который мы ожидаем запуска в 2022 году, это проект Луна-25. Это первая мягкая посадка России на Луну за 40 лет, начиная с больше чем за 40 лет, начиная с середины 70-х годов. И это будет, будем надеяться, первая мягкая посадка в приполярную зону вообще в мире, значит, если мы полетим в июле. Здесь существует большая конкуренция, кто первый сядет в приполярную зону, где условия для посадки несколько сложнее, чем все прошлые места посадки в экваториальной зоне. Здесь мы практически, космический аппарат уже собран, протестирован, и завершаются заключительные операции, чтобы отправить его на космодром с запуском примерно в июле. Следующий, пожалуйста. Третий запуск, который мы ждем в конце 2022, может быть, в начале 2023 года, это запуск двух пар, на самом деле, 4 малых космических аппаратов для мониторинга ионосферы. Местный проект России и российской науки, и российского метеослужбы предназначен для мониторинга верхней атмосферы. 2 аппарата будут запущены в конце 2022, начале 2023 года. И, возможно, через год еще 2 аппарата, примерно через год, будут запущены. Следующий, пожалуйста. Теперь, кроме того, у нас существует большая программа научных экспериментов на Международной космической станции. Если мы говорим об исследованиях Земли и космоса, не учитывая медицину и технологии на борту, то это более 40 экспериментов по всем основным объектам Земли и космоса, начиная от исследования океанов и заканчивая исследованиями рентгеновского фона Вселенной. Следующий, пожалуйста. Что нас ждет в перспективе с 23-25 годов и далее? Прежде всего, это те проекты, которые в Федеральной космической программе упомянуты с запуском до 2025 года. Это возвращаемый аппарат Бионем с биологическими и технологическими экспериментами на борту, который должен вернуться на Землю через 2 недели после запуска. Это лунный орбитер Луна-26 с запуском конец 2024 года. И следующий за ним космический аппарат Луна-27 для точной посадки и исследования лунного реголита в полярной области. Я прошу прощения, здесь только год неправильно указан, должен быть 2025, а не 2027. Также мы ожидаем готовности к запуску малого спутника для исследования магнитосферы резонанс и еще одного большого крупного международного космического проекта, это ультрафиолетовый телескоп Спектр УВ, который должен быть тоже запущен в 2025 году или чуть позже. Это тоже проект с большим международным участием. Следующий, пожалуйста. Если говорить о более дальней перспективе, то мы видим, во-первых, исследование, как основные приоритеты российской программы, это исследование Венеры. Это участие в индийском венерианском проекте с российским прибором Вирал, это примерно середина 2020-х годов. И это и запуск такого флагманского проекта российского Венера-Д с посадочным аппаратом и аэростатом в конце 2020 годов. Также в планах проект АРКа, проект малого солнечного телескопа, проект «Спектр-М», о котором сегодня, я знаю, будет много информации представлено. Это миллиметровый телескоп для интерферометрии в этом диапазоне исследований дальнего космоса. И это проект Гамма-400. И это проект Гамма-400 для продолжения исследований высокоэнергичной Вселенной в гамма-лучах и в рентгеновском диапазоне. Таким образом, я дал сейчас такой краткий обзор российской космической программы в ближайшие 10 лет. Следующий, пожалуйста. И, конечно, мы сейчас активно обсуждаем и не только и научные эксперименты, но и технологический задел, который наука должна создать для продолжения освоения Вселенной. Это, так, я прошу прощения, это полуденный выстрел на Петропавловской крепости в ознаменование российско-корейской дружбы. Значит, это создание технологий и полезных нагрузок для сверхтяжелой ракеты, это космическая ядерная энергетика, это искусственный интеллект в космосе и создание многоспутниковых группировок. Спасибо за внимание.
Спасибо большое, Анатолий Алексеевич. Следующий докладчик будет представлен нашими корейскими коллегами. Korean colleagues, please.
Yep. Next speaker is actually myself. I'm Taehyun Jung from Korean.
Нет, у меня есть. Как только это самое.
May I start?
Sorry, this is a previous speaker still in online. Анатолий Алексеевич, отключитесь, а то вы там разговариваете, нас перебиваете. Okay, please continue. Sorry.
Yeah, okay, thank you. And I'm Taehyun Jung from Korea Astronomy and Space Science Institute. And then I'm very honored to be here and having a chance to introduce our collaboration with the Russian friends and based on our Korean VOVI network activities. So I will start introducing the Korean VOVI network. As you can see here, the three 21-meter diameter class radio telescope is located in the Korean Peninsula, and one is in Seoul, and the other one is Ulsan, and another one is Hamna in Jeju Island. So we have using this three radio telescope, we form a virtual big size radio telescope, like a maximum diameter around 500 kilometers between the Jeju and Seoul area. So based on this VOVI, very long baseline interferometry technology, and Korean VOVI network observe astronomical sources observing frequency from 18 gigahertz up to 150 gigahertz, which is corresponding to the wavelengths from 2 to 14 millimeter. So actually, let me shortly introduce about the VOVI. VOVI is a special technique to achieve high angular resolution in astronomy by combining the specially distributed radio telescope into as a single virtual radio telescope by observing the same source at the same time. And then observed data recorded onto the disk bag at the individual radio telescope. And then later on, we synthesize this data as to form a single virtual focus of the VOVI network. So this KVN telescope, as a single dish, we can achieve 120 arcsecond in resolution. But if we work, use this radio telescope as a VOVI observation mode, that provide 20,000 times better angular resolutions in VOVI mode. So this is particular specific technique, VOVI, is better. We get better angular resolution if we combine more, radio telescope in further away. So here you can see the around the China, Japan, and also Thailand recently joined. And then actually, I'd like to make a note that we have a good VOVI observation history with the Russian Quasar VOVI network here, together with the EAVN and also the KVN. And so after this 45 observations since 2020, and then Quasar network data coming to our correlation center at our headquarters, CASI, and we study the astrophysical and geophysical phenomena in the universe. So, as you remember, in 2019, we firstly captured the black hole image of M87 elliptical giant galaxy. This supermassive black hole, which resides at the center of the M87 galaxy, distance is 55 million light years from Earth, and then black hole size is around 40 billion kilometers across, and the mass is 6.5 billion of the sun. And this Event Horizon Telescope actually achieved Earth-sized telescope by connecting a global network of radio telescope like this, and then 20 micro arcsecond resolutions at 230 gigahertz observing frequency in 1.3 millimeter in wavelengths, accessible to the central region near the black hole. So that's how we get this image from the Event Horizon Telescope collaboration. And actually the KVN and EAVN also participated in this campaign in 2017 on behalf of the multi-wavelengths campaign of the EHT project. The millimeter wavelengths VOVI, as you have seen like that, is quite important and also provide the most high angular resolutions. And also this allow us to explore the central region of the astronomical object, for example, near the black hole or some star-forming regions or evolved star region in many astrophysical environment. As you can see, if we shorten the observing wavelengths, we can reach the central region of the black hole. This is a specific diagram which jets, astrophysical jet coming from the black hole to the outside. So if we observe a higher frequency, that allow us to observe very vicinity of the black hole. So, however, this millimeter wavelengths, high frequency VOVI is quite challenging and difficult because generally the sources, the lights are fainter at millimeter wavelengths, and also it's very essential for having a high precision radio telescope and receivers and subsystems. And millimeter VOVI is quite, severely suffer from high system noise temperature. However, this kind of technological difficulties has already overcome by recent advances in radio technology. But the sky condition, which is unavoidable for this millimeter VOVI, is still remain as a main difficult. This atmospheric effect in the ground, we cannot avoid when we observe the light from the astronomical universe sources. So if we observe higher frequency, that because of the atmosphere, it shortened our coherence time, which means we cannot integrate the object, the radio source, as much as we can. If we go to the 129 gigahertz VOBI observation, theoretically, and the possible integration time is only about 10 seconds. This means we cannot get a good signal-to-noise ratio for when we observe in this millimeter VOBI observation. So Korean VOB network introduced unique innovative system for millimeter VOBI, which is a multi-frequency receiving system. With this system, we observe the different frequency band at the same time. And also now it's much smaller, 1/10 in size has been developed. And then this one is widely spread to the other millimeter VOBI network in the world. So this multi-frequency receiving system in VOBI observation has a great benefit because we can observe multiple radio frequency bands simultaneous so that we can get multiple information from the source. And then this can increase the telescope time efficiency dramatically and together with the observation outcomes. Detailed for this system will be presented by Dr. Han later. The basic principle is like that. If it comes from the source, the radio signal coming from the source, it comes to each telescope at the same time. But we can observe 22, 43, 86, 129 gigahertz at the same time. By then, we use, lower frequency phase VOBI information to calibrate high frequency VOBI phase calibration. This is this is basically based on the non-dispersive nature of the troposphere. This system is ideal for removing such atmospheric turbulence in the atmosphere for millimeter VOBI observation. So this system now offers a new millimeter VOBI sky in the universe. Here we have quite many sources, around 20,000 sources at centimeter VOBI wavelengths, which is available. But here, if you can see 3 millimeter VOBI observation, only 116 sources has been detected. However, with this system, by adopting our, simultaneous multi-frequency system together with a unique novel calibration technique, we can detect more than 4 times larger sources at 3 millimeter, and then 347 sources also available at 2 millimeter. This is the largest number of sources in millimeter VOBI detected by the KBN. And this system is now spread widely in globe. Currently, Italian stations are already, introduced our system, and Finland and Tianma is going to be implemented, YEBES already, and also the Japanese VOBI network is also adopted. So we are doing, based on these multi-frequency capabilities at millimeter wavelengths, I'm sure that we can make a very good synergy with the Millimetron Space Observatory in the future. With this Millimetron telescope, and we have a quite, common frequency range from 30 to 100, 250 or 370, and the space Earth VOBI observation will give us unprecedented angular resolution up to 10 to the minus 8 arc second. This provides a very unique scientific result as a representative tool source of the closest black hole, Sagittarius-A, and also the largest black hole, M87. And with this millimetron, together with the ground station, we will be able to resolve an imaging event horizon scale structure that can provide unique information about the jet formation and fundamental black hole parameters. And particularly, I mean, these lower frequency observations, simultaneous lower frequency observation will be very, critical for delivering solid fringe detection and information for millimetron higher frequency observations. And also this system with the millimetron and multi-frequency system with the millimetron and ground telescope can calibrate the observing data quite well so that we can improve our observed result quite much. And then this special technique developed by our colleagues and will give unprecedented accuracy for event horizon scale astrometry, for example, core shift measurement of Sagittarius-A or M87. Okay, so let me close by introducing this one. And so KVN, we are now constructing the one more telescope in the Pyeongchang area here, and which is capable of observing 230 gigahertz at the same time, simultaneously. So this EKBN project, EKBN telescope, which will be constructed in 2023, will be a good pathfinder for ground testing such a calibration and system demonstration in ground for the millimetron, and also will be a key telescope when the millimetron has launched it to make a space ground VOVI observation in the future. Actually, we have a quite long history. Korea-Russia collaboration in VOVI has been made since 2014, and KVN telescope participate in the radio astron observations, and we have successful detections and results. And also we have a good, friendship between our colleagues and memorandum of understanding and collaboration. And actually last month, we had a very successful Kashi Aerospace Center millimetron workshop. And also now we are continuing the designing of the millimetron multi-frequency system, as well as multi-frequency calibration science working group activities together with a Russia friend. Thank you for your attention.
Thank you very much, Dr. Tae-Hena Chon. Now the next speaker is the head of Astrospace Center of Physical Institute of Russian Academy of Sciences, Sergei Fedorovich Likhatchev. Please, Sergei, as you prefer. Maybe he's better.
So the microphone is working. Okay. So, dear Mr. Chairman, dear colleagues, ladies and gentlemen, let me introduce myself. My name is Sergei Likhatchev. I'm the director of the Astrospace Center and the PI of Millimetron Mission. Since our Korean colleagues and Professor Tae-Hyun Jang already talked everything about Millimetron, I will be brief. So the collaboration between Astrospace Center and Korean Space Science and Astronomy Institute, KASI, was started about 7 years ago after the launch of radio astronomy mission. And our Korean colleagues works with us by means of Korean VOVI network, KVN, and we have got a very wonderful results in multi-frequency observations. It's a very rare technology that Korean and Russian scientists are going to develop currently. Then our collaboration was prolonged by with the Millimetron mission. The Millimetron mission is a very promising and very significant project, space project of the Russian Federation, and it is included in the Space Federal Program of the Russian Federation. And we are very pleased that our Korean colleagues have shown their interest in the collaboration and cooperation with the Millimetron mission. We respect very much the experience that Korean scientists already obtained with the millimeter VLBI, since the Korean technologies are well known all over the world. And I really hope that our cooperation will be fruitful in terms of creating onboard electronic equipment like multi-frequency CDS observation of in the millimetron band, and also as a ground space support of the millimetron mission. My colleague Alexey Rudnitsky will present you current status of the millimetron mission and our vision of the Astrospace Center in a further collaboration with our Korean friends. Thank you very much. That's all. 감사합니다.
Thank you very much. Dr. Likhachov finished, and now the next speaker is again about the Millimetron mission. Rudnitsky Alexey Georgievich. This is the Laboratory of Ballistic Navigation providing of space missions, Astrospace Center, Physical Institute of Russian Academy of Sciences.
Okay, thank you very much, colleagues. So with me, okay. So greetings, dear colleagues, ladies and gentlemen. My name is Alexey Rudnitsky. I am also a deputy head of Astrospace Center of Lebedev Physical Institute. Today I will give a short insight on the Millimetron mission and our cooperation with our Korean colleagues from Korean Astronomy and Space Science Institute, KASI. So our cooperation can be divided into main directions. Right now, the first one is the Millimetron Space Observatory, which is led by Astrospace Center, and the second one is the opportunities for the development of ground millimeter astronomy in the Russian Federation. So the Millimetron Space Observatory actually a unique project. It's a sub-millimeter, millimeter, and far-infrared space observatory with a 10-meter deployable and actively cooled antenna. It will operate in two modes, as a standalone telescope and as a part of space ground interferometer, so-called VLBI mode. The spacecraft will be located at Lagrangian point L2 of Sun-Earth system, which is 1.5 million kilometers away from the Earth in anti-sun direction. The concept of the observatory assumes the solution of the most actual and innovative problems in the field of astronomy and astrophysics. Thus, we have selected 6 directions and founded 6 scientific working groups for each of the key science topics. And each key science topics is like a Nobel Prize level. Since we are talking primarily about the interferometer mode, because our collaboration with our Korean colleagues devoted to the big experience of both sides in this field of astronomy, the Millimetron will give a unique opportunity to get an unprecedented angular resolution with its orbital configuration together with ground telescopes. And thus also in turn taking into account such large aperture as a single dish telescope, it will also give an opportunity to perform a breakthrough studies in the field of astrophysics. So our Korean colleagues from KASI have a great experience, as already you have seen in the presentation of Tayun. A great experience in developing the multi-frequency interferometry. So this is one of the key cooperation topics. The next one is that KASI is participating in practically all scientific working groups of the Millimetron space mission. This means that we're defining together the key scientific problems and directions to be solved within the Millimetron Space Observatory. The next one is the point that we are currently discussing together. It's a very promising point about the development of the ground size on the territory of Russian Federation, ground size for millimeter astronomy. And finally, we consider the studies of the possibilities for onboard development of the memory supply for the Millimetron Space Observatory, with the possible involvement of profile companies. Still, it's under consideration. Multi-frequency observations, as already mentioned, provide unique opportunities for improvement the interferometric mode observations itself. This means the increasing of the dynamic range of the image, its quality, and in general, this mode dramatically increases the quality of the scientific data to be obtained in VLBI mode. Thus, we consider as one of our main directions of cooperation, we consider the development of quasi-optical system for Millimetron Space Observatory by CASI, and we hope to have a corresponding agreement under Roscosmos and CASI on the development of this instrumentation. But before this, we had great expertise and joint cooperation of multi-frequency tests starting from the Radiation mission. Actually, it was, I think, the first and the only space ground VLBI observation that was done with Radiation, and it was successful, together with the Korean VLBI network, KBN antennas. However, these observations were carried out in the radio, not in the millimeter wavelength ranges, but we see that these capabilities are very promising, not only for the space ground VLBI, but for ground VLBI as well, like next generation Event Horizon Telescope antennas. So it is more likely to expect that practically all radio and millimeter ground antennas will try to get these multi-frequencies capabilities very soon. However, speaking about the space, we need to think about the ground, because space interferometry without ground telescopes, it's not an interferometry itself. Thus, we performed also ground tests with ground facilities. First of all, it's a Pushina radio telescope, and we hope to have more of them. And obviously, we come up to an idea that the development of millimeter size on the territory of Russian Federation, and not only on the Russian Federation, it's very important for the space mission like Millimetron. Thus, there is a SUFA project that you have already heard about it, but it's a 70-meter antenna operating at millimeter wavelengths will be located on the SUFA plateau in Uzbekistan. However, there is a consideration of a smaller antenna to be built before on the same site for ground tests, and I think that multi-frequency capabilities will be important here. However, we performed the simulations to prove that multi-frequency observations on the ground are very important for the science. And what's next? Next is to think about the development of telescopes on Russia that will be capable of observing in millimeter wavelength range, and to have a multi-frequency support, of course. So thus, we are considering it to exchange experience and cooperate in this area with CASI as well, not only in millimeter. Summarizing my overview, the cooperation between CASI and Astrospace Center, as was mentioned by Sergey, lasts for 7 years already, and it brought into VLBI astronomy many new results, mostly regarding about the tests and observations in the multi-frequency. And currently, the development of the global VLBI astronomy, I speak about the ground astronomy first of all, and scientific tasks that are stated behind this technique shows the necessity of development of the multi-frequency capabilities in millimeter mission and as well as for ground telescopes. So we see here the need for the development of ground-based millimeter astronomy telescopes in Russia. And we hope to have a cooperation with our Korean colleagues here as well. Taking into account all these facts, we expect that successful cooperation within a millimeter mission and within the development of ground telescopes of millimeter wavelength range in Russia can set the tone of the global millimeter wave astronomy for the next several decades, I hope. So that's all. Thank you very much.
Thank you very much, Sergey. Alexei Rudnitsky. Now the Korean speaker.
Thank you. And next speaker from Korean side is Dr. Seok Tae-han. He will from Korea Astronomy and Space Science Institute. He will give a talk about quasi-optical circuit design for millimeter wave multi-frequency band receiver system. Thank you.
Good morning and good evening, everybody. My name is Seok Tae-han to the Korea Radio Astronomy Space Science Institute. It's KASI. So, what I'm talking about today talk is the history of a multi-band receiver and also quasi-optic circuit design. And also now we have some projects to develop a compact triple band receiver for Italy radio telescopes. Finally, I make these discussions. And so conceptual design for the simultaneous observation for multi-band receiver, it comes out maybe 19 years ago, 2003. So as you know, the millimeter wave VLBI over the decade has been intensively conducting so far. However, problem is the signal-based fluctuation due to the atmosphere or water vapors. It turns out the degradation of the sensitivity and imitation of the image capability in millimeter wave VLBI observations. In order to overcome such kind of problem, I was thinking about how to overcome such kind of problem, and also I proposed this kind of a simultaneous millimeter multi-band receiver system was proposed in April 2003, just like almost 19 years ago. Let me briefly introduce how to make the simultaneous observation by using multi-band receiver. So a receiver, I mean the 22 and 4386 129 gigahertz comes down the subreflector of the Cassegrain antenna, and also the for 22 gigahertz goes through the Lopez filter 1 and back goes to the 22 gigahertz. However, these 43 gigahertz and 86 129 gigahertz reflected by Lopez filter, and also such kind of beam illuminated by using ellipsoidal mirror, then goes through the Lopez filter, then 43 gigahertz. And 86, 129 gigahertz reflected by Lopez filter, and reflected by ellipsoidal mirror goes to the 86 gigahertz. And also finally, 129 gigahertz reflected by Lopez filter, and deculminate by ellipsoidal mirror and goes to the 129 gigahertz. Can you imagine how to operate, how to make the simultaneous observation through these pictures? Okay, and it took a very long time to develop such kinds of the multi-band receiver. It takes about 8 years. from the April 2003 to the May 2011 to until the first light by using the multi-frequency receivers. I think it is first developed in the world. So I'm very proud of this, such kind of receiver has been conducting VLBI observation for KBN and also global VLBI network since 2012. This is one of our KBN sites for the this is the Yonsei University in Seoul. You can see this is a real 4-channel multiband receiver. So can you imagine how to make the observation? It's a very complicated optical bench. You can see 22, 43, 86, 129 gigahertz, and also there are 3 low-pass filters. Actually, beam goes down to from subreflector and 45-degree mirrors, something like that. So anyway, it is very complicated. So as you know, the current KBN receiver, which is the 4-channel multiband receiver, as you can see, it's approximately 2.3 meters and 2.6 meters. It is too large, too big. So in KBN receiver, cabin has been designed to be installed in such kind of receivers. So, however, some antenna which can make which can be installed in such kind of the receiver, as you know, is the space is quite limited and very small space to be installed such kind of multi-channel receivers. So that is one of the motivation reason why I have to try to develop much more compact triple band receivers. So conceptual design, it came out the April 2015. So finally, successfully, and the test observation was done September 2018. It takes over 3.5 years. So triple band can make observation for KQW band. You can see this is a real prototype compact triple band receiver. So you can see 600 by 600, height is 370, optical length about 380 millimeters. So, okay, and okay, oh, I'm sorry, this is a 2 slide. Okay, and when we make a quad-optic socket, which will be used for the compact triple band receiver. So when we design quad-optic socket design, it is very critical tools to realize the multi-band receiving system. So in order to make the maximum antenna efficiency, so we adopt the frequency independent image beams. It is based on the Gaussian beam propagation property. There are 3 frequency independent image, which I frequently, quite often use when I design quad-optic socket for millimeter wave receiver system. And there are 3 kinds of the quad-optic design tools. First is the stationary frequency independent beam waste, and secondary is a stationary frequency independent image beam, and also achromatic doublet. There are 3 main tools to design the quasi-optic circuit. So I don't want to talk about more details. If you are interested, you can refer 3 kinds of papers. So this is a real quasi-optic socket for CTRs, for Italian telescopes. And now we are developing 3 sets of the compact triple band receiver for 3 Italian telescopes. So when I design the quasi-optic socket, as I told you before, I choose the frequency independent image to obtain the maximum antenna aperture efficiency. for Q and K band, there are some dielectric lens. And also the beam goes down there are two Lopez filter, 1 and 2, and also for K band, dielectric lens and elliptical mirror. For W band, there are 3 elliptical mirror, 1, 2, 3, and also 2 frame mirror. This is a real design, the quasi-optic circuit, including the cryogenic chamber. As you can see, the width is about 350 and the length about 800, and chamber about 600. It means that the total length of the compact triple band receiver is about 1400 millimeters, and width about 750 millimeters. So even though we are designed by using Gaussian beam propagation design, we have to evaluate or optimization by using graphs, which is very famous and also very powerful tool to evaluate the Gaussian beam or quasi-optic circuit. So we use the ideal Gaussian beam waste instead of a feed horn, real feed horn. And also finally, we reconfirm by using actual radian pattern of the feed horn. So there was, this is a K band. You can see as this is a lens, and also this is a Q band and the lens and mirror and W band. You can see there are 3 elliptical mirror and 2 prime mirrors. So anyway, it's a graph is very useful. I emphasize that the graph is very powerful, very useful, very gameful to evaluate real quasi-optics. Okay, this is one of the results for evaluation quasi-optic circuit for by using graphs. So we can achieve the maximum antenna aperture efficiency. K band is 77%, Q band 77%, W band 78%. You can see it's a very constant aperture efficiency in terms of the each band. The reason why we can have such kind of constant aperture efficiency is it turns out the frequency independent imaging method, as I told you previous my presentations. So and also another is a very important item is the cross polarization. When you make a VLBI observation, it's as you know, it's a cross polarization property is very critical. So when I design quasi-optics, I focus on how to reduce the cross polarization. It's very pretty good. So K band minus 55 dB and Q band 25, W band 30 dB. Those kinds of the cross polarization loss mainly from the elliptical mirror and anti-refraction lens. I mean the dielectric lens. So okay, this is a copolarization radiation pattern. This is cross polarization for 22. This is a copolarization and cross polarization, and the copolarization and cross polarization for each band. So this figure shows the real quasi-optic circuit. This one is this design the three-dimensional something like quasi-optic circuit. This is a real quasi-optic circuit. You can see there are 2 Lopez filter. Lopez filter 1 reflected by W band and the transmission K and Q band. Lopez filter the refraction for the Q band and transmission for K band. You can see there are 2 K band and the electrolyte lens. The lens was fabricated by the material for electrolyte. It's a dielectric constant about 2.5. So, and also, such kind of lens is a very critical item is the refraction of the surface. In order to reduce the refraction loss, we have the Whopper structure surface for the anti-refraction. Such kind of anti-refraction, it is very critical in terms of the reachable noise temperature. So anyway, total polarization at the quasi-optic socket about -55, and the insertion loss less than 43 dB, including the range, mirror, Lopez filters. It's quite good in terms of this noise temperature, even though it is operate at room temperature. Okay, it is very important beam measurement system to evaluate whether Gaussian beam is we can compare between the theoretical and the design value for such kind of cross polarization, and also the beam radius at each point. So in order to evaluate to such kind of quasi optics, we developed the beam measurement system. It is available to frequency 18 gigahertz to 250 gigahertz. By each changing each model, such K, Q, W, and D band, and also 25, 250 gigahertz. And also we have another beam measurement system which can be available to measure the 27 to 50, 270 to 500 gigahertz. It is a very high frequency for the beam measurement system. By using beam measurement system, we can do to measure the beam pattern for individual lens, and also Epsilon mirror and Peter horn, and also total quasi-optic socket. It is very useful to evaluate and also to investigate the such kind of quasi-optic component. And also we can measure the cross polarization, which is very critical in terms of the millimeter wave BLVI observations. So let me introduce very briefly current status of the compact triple band receiver for Italian radio telescopes. So specification of the compact triple band receiver is the we can have two channels, RHCP, LHCP, and also simultaneous full RF band, the 18 to 116 gigahertz just by one shot. One shot means just one observation. It is very powerful to study on the cosmic waves. So, and also the noise marker injection capability to calibrate the antenna and receivers, and also single observation, BLVI observation, and also sun observation as well. So this is the frequency range and specification of the visual noise temperature is about K band 60 Kelvin and Q band 70 Kelvin, or W band less than 100 Kelvin. So this is a cryogenic chamber. Now we are installing the some of a module. It's a vacuum. Already we achieved the 10 to -7 torques, the temperature less than 20 Kelvin. So now we 3-band the modules are installed in cryogenic chamber. Okay, this figure shows the very critical component to make the observation. So this kind of PD system consists of the feed horn and phase shifter, OMT, and power divider, and copper. So total loss of the is about less than 0.5 dB for K and Q double band, and W band less than 0.8 dB. It is quite good. And also cross polarization less than the 30 dB. Okay, so this is a final slide for the discussion. It's a project for compact triple band receiver for Italian telescopes has been going well so far, and it must be delivered to March next year. So Arado ground station, I think then in near future, there are a lot of ground station which is equipped for CTR, for millimetron, and some international VLBI for Korean, Italy, Spain, and Finland, something like that. So in order to develop more high frequency, which is the 80-230, 345 gigahertz for the new generation EHD or millimetron, we have to need more research how to develop such kind of high frequency for compact triple band or simultaneous observation, those kinds of frequency range. So I strongly emphasize that in order to develop more high frequency for CTR for both ground and space radio telescopes, such kinds of the millimetron, we need more sustainable and tangible project to develop key component, as I told you before my slide, such like key components which will be used for the space environment conditions. Okay, thank you very much for your attention.
Thank you. And next
Thank you very much, Dr. Han. Thank you. Next speaker is the director of the Kotelnikov's Institute of Radioelectronics, Radiotechnics and Radioelectronics, Nikitov Sergei Apollonich, correspondent member of Russian Academy of Sciences. Instead of him, there will be another speaker. Directors are always busy.
Hello, everybody. My name is Valery Koshelets. I will talk presentation from our institute, which directed by Sergei Nikitov, and it's a pleasure for me to talk about superconducting coherent receivers for ground space and for ground-based and space radio astronomy. And this is outline of my talk. Actually, it's 3 different parts. Firstly, I will talk about development which we for the frequency range of 211 to 275, which intended actually for millimetron mission, and also very briefly about development of high frequency receivers which installed already on Apex telescope in Chile, near Atacama, Alma project, and a couple of thoughts about for switching for what? Okay. Okay, so SS mixers is definitely the best input devices for high frequency applications. So actually their noise temperature is limited only by quantum limit. And this is here you can see IV curve of the such junction, and actually they used quantum effects. It's quantum tunneling, and as a result, it's possible to realize really very low noise temperature and very wide frequency range, so up to from 0.1 probably up to 1.4 terahertz. And to realize this performance, we need to use very high quality junctions. So this noise, this leakage current below depth should be as low as possible. And to match these devices with input this antenna. We need very high current density junction to realize wide bandwidths. And for that, we use traditionally niobium aluminum oxide or niobium aluminum nitride junction with current density up to 30 kiloohms per square centimeter and with very low leakage current. And important that this very thin layer of tunnel junction is actually very high capacitance, which should be tuned out on the high frequency. And this is just a few examples. So SIS receivers is now used in most radio telescope, and already mentioned example of event horizon telescope and two large radio astronomy arrays which used for such observations. And another example, this is Millimetron, which was presented just by Alexei and Rudnitsky and Sergei Likhachov. So this is, as mentioned, there are two different modes of operation: single dish telescope and space Earth VLBI. And for this VLBI operation, there is a so-called band 3 now in the Millimetron, which is 211, 275 gigahertz, and single sideband noise temperature should be below than 45 K according to specification. And the reason for this development is that even with using the telescopes situated in different places on the Earth, it's impossible to get good enough angular resolution to increase the base of this. The one telescope will be placed in space on the L2 orbit, and second one we use ground-based telescopes. And to achieve this goal, we actually developed the first prototype which can be used for this mission. So we developed a double sideband receiver, and this is 3D design which we used by CST made, and experimental data which demonstrates that really the desirable frequency range is available right now. You can see here two FTS data measured for two different devices, and on the left side you can see the models which we use for development of mixer block and so-called backpiece, which where the tiny junction is mounted. And to realize all this performance, as I already mentioned, the very high quality junction with small area are required. Furthermore, it appeared that to realize noise-free operation and stable operation, it's important to get very actually ideal IV curve of the junction. And to reach that, we developed new let's say new technology, which so we introduce additional aluminum layer in the niobium aluminum oxide junction very close to the tunnel barrier. As a result, almost ideal IV curve it's appeared. You can see here the ratio gap and more resistance 37. It's actually very good result. And this is already results of noise temperature measurement. So we used hot 30 room temperature and 77 K loads, and the difference between these two responses is as high as 5 dB, which correspond very low noise temperature. So you can see here dependence of the noise temperature on the frequency, and actually it's the whole range. The noise temperature is quite low, and it's in the double sideband regime, it should be multiplied by 2 to compare with the requirements. And nevertheless, it's really good and almost reach the quantum level, which is marked by red line on down on this shot. But this approach is valid only for frequencies below, let's say, 700 gigahertz. At higher frequency, niobium becomes normal metal, and it's produced some additional losses. So to realize receivers which can operate at frequencies about 1 terahertz, one need to use some other approach, and one of the possible and actually now commonly used. First of all, we developed a high-quality junction with higher gap frequency, which is based on niobium, aluminum nitride, niobium junction. And in this case, area should be as low as 0.5 square micrometer. But secondly, this junction should be inserted in microstrip, which can operate at frequencies about 1 terahertz. So in this case, it's niobium titanium nitride ground layer and aluminum top layer. And this is IV curve of this junction and a photo of this system. And noise temperature, in this case, of course, it's a little bit larger than before, so we can reach only 3 quantum level, but it's still very good value. And these junctions were used for development of next generation for Atacama phosphide experiment APEX, which installed in 5 kilometers about that in Chile, and it includes 2 different receivers, 7 pixel receiver for each frequency. And in our case, we developed devices for frequency range 780, 950 gigahertz, and you can see here the antenna and 7 pixels, actually 7 horns, small horns in this system. And that is how looks the single pixel, and all together mounted with lens on to match it further. And noise temperature, which can be realized, is below 400K in the whole range. It's new pixels which were developed for replacement to upgrade. We marked by red color, and the previous version is by blue one. And it's possible to see, first of all, recover the whole frequency range which is required, and secondly, improvement in 1.4, 1.5 times actually give possibility to decrease observation time in 2 times. So this is very briefly technological facilities which we have at IRI to fabricate this junction, because everything which was demonstrated here was fabricated at IRI, Kotelnikov IRI. This is Putlesker 2-section, 2-cluster system for fabrication of the junction. This is electron beam lithography system that's used for fabrication of the photomask and junction itself. And this is circuits which can be fabricated. And what I mentioned is very high current density is available by using this technique. So in conclusion, we have developed technology fabrication, very high quality junctions with high current density, which can be used for very low noise receivers. And 2 mixers were developed. First, this is prototype for millimetron mission with frequency range 211, 275, with noise temperature below 20K, which actually satisfies the requirements from the millimetron, and new generation of such devices based on higher frequency junctions mounted in special niobium titanium nitride light with much higher operation frequency were developed and installed on the telescope. And so this is just demonstrate again that our fabrication technology, this fabrication technology is mature enough to satisfy the requirements for the ground based space mission. Thank you for your attention.
Thank you very much, Valery Pavlovich. Very impressive results for astronomers. Okay, and the last speaker will be given by Korean colleagues.
Yes, the last speaker from Korean side will be is the Kim Kyung-cha from Korea Institute of Geoscience and Mineral Resources. The title of the talk is A New View of Lunar Resources Originated from Solar Wind and Its Significance. Let's welcome to the speaker.
Hello, can you hear me?
Yes, we can hear you.
Thank you. So, yes, I would like to introduce lunar resources originated by solar wind. And there are 6 missions involved in water discovery on the moon, like Clementine and Lunar Prospector, Chandrayaan-1, ECROS and ERARO and LADEE. And the SOFIA is not the mission, but the observatory of aircraft by NASA. And I could say water ice at the polar regions. The source could be impact with comets and meteorite and solar wind implantation and outgassing our lunar interior, such as volcanic activities. False kind, I don't think that's well confirmed. I would like to introduce water on the moon as a chronological order. So Clementine in 1994 suggested there could be permanent shadow region on the polar regions, so which means this is very, very cold. So all the meteorite and comet deposited could be just stay there with a very low sublime rate. So that was just suggestion of the water. But that is confirmed by Lunar Prospector in 1998 with the neutron spectrometer. So at least 4.6% of water on the North Polar region and 3% of water South Polar region with a detection limit about 0.01% water, which is very, very accurate the nuclear instrumentation suggested by Los Alamos Group. And interestingly, I was also very shocked or very interesting me for this kind of result that Chandrayaan-1 provided, how the moon produced its own water with the SERA instrument collaborated by ESA and ISRO. So to study the moon surface composition and solar wind surface interactions. So measuring solar wind, instant solar wind, and then also the energy of the ion is sputtered with a certain energy that will confirm this kind of production of the water on the surface. Interestingly, this Chandrayaan-1 has MQ made by NASA's payload actually, and that confirmed that with the altitude increase, the more relatively more water present, water and hydroxide molecules. This was a very interesting one. Not only the polar regions, but also the far side of the moon, very young lunar crater also have this kind of water signature, hydroxide or water. So this means water could be many other places rather than polar regions. And additionally, the ECROS and ERARO mission together, it was very interesting mission for everyone. and searching for the water ice by impacting of the spacecraft partially. So importance of searching for water on the moon is to reveal the origin of the volatile element and utilize resources in manned future missions. So that is what's happening for Artemis mission 3. And the aircraft, the weight of dropped was actually 3,000 kilograms, like a bus size. And then from that impact size, the water content was at least 5.6% of water, and then many other molecules are absorbed. And these could be resources for future utilization. And detection of water in across ejecta fume also confirmed that not the right after impact, but 23 to 30 seconds, we have a more increase of a significant increase of the water signature. And then it lasts for 3 minutes. And another important mission, the payload for water detecting was land neutron detector experiment provided by Russian group. And this one really shows that the impact site, at least 0.5 to 4% of water ice by weight present, depending on the thickness of the surface layer. But this is not that different than the lunar prospector. And so because of this kind of previous discovery, geologists really suggested through ISAC report where we could possibly land in South Pole region. So at least the Cabeus region is very good place to go, considering water, PSR as well resources, and then water visibility and sun illumination and slope as well. So these are 5 criteria we have to concern. But if we think about the North Polar region, is much wider regions we could go to stay longer for human and establish base. So this is very interesting, and I heard that at least the Peary region has 100% of sun illumination. This is a really good site to go. And if we think about the water, actually we also mentioned about the volcanic origin. So especially Apollo 17 landing site, and from the subsurface, you could see many different kind of color with the different composition. So especially soil 74220 has the volcanic glass feed, and that if that was heated, and then you can see that the water and the many other molecules were extracted. So these could be resources. So like a fountain, lava fountain on the Earth space. So because of this kind of water resources, geologists really draw map as a lunar pyroclastic deposit, and then investigated the water content. So these are at least some red places really more than 0.3% of water present. So this could be places to go. So another, for me, I also very interested that LADEE was launched in 2013, but 2019, actually this very interesting research result was published by this LADEE group, that actually water is coming from solar wind, and then is go down to the subsurface water, and then when meteorite impact, the water actually comes out. So which means many places we have a water, subsurface water. So water is not only present in polar regions, but many other places on the surface. Very interesting results came last year, that the M-cube actually shows only hydroxyl and water together with the 3 micrometer the wavelengths, but the SOFIA really shows the 6 micrometer signature with the discovery water at the Clavius crater. But this is only water, no hydroxyl signature. And it has more water present than this, the M-cube discovery, which means probably we have more water than we have discovered by the scientific instrument. So that is what we really now consider the future. So molecular water detected on the sun-lit moon by Sophia. This is interesting. The publication Nature Astronomy. So that really shows the 6 micrometer band properties, shows moon and meteorite, and some middle region areas, or also crystalline the mineral itself. That shows very similar signature. And then this discovery is a very good discovery that we really consider where to excavate our resources from the lunar surface. So I would like to show one short video. This is very interesting, and that summarizes that we could go many other places rather than possibly let me see. So main point is water present all across of the lunar surface, but that could be depending on the surface composition a little bit. So because I work on nowadays lunar resources institute, lunar ISRU, now consider where Korea should go for future mission, and I consider past the location of the landing and crash site of the moon. And then more, I mean, the left side, you can see Apollo program and lunar program, and additionally China program. So now I think about future lunar base or future exploration, water illumination, water visibility, and PSI and volatiles should be considered. And however, I think also the PRE region, we have 100% illumination, so probably the best place to go. However, I don't think we should ignore any the other regions where we have more water present, and possibly some other features can be utilized for us to investigate and make a base. And then another thing I mentioned this graph that the maximum the stayed in Apollo program was about 30 days. Now we want to stay more than at least 10 days for Artemis 3, and then more like a 1 month stay or much more longer. So that is our situation. So water is widely distributed across the lunar surface, and volatiles can be obtained from the lunar regolith, and the utilization of lunar resources promises for humans to go longer stay on the moon and beyond. So we have to overcome 2 conditions for lunar base in the polar regions: Earth visibility for communication, and sun illumination for temperature and solar power. Some other, I'm very interested in, of course, I mean, polar region is the best one, but I'm considering whether there are other places to actually investigate. So the maximum stay, 30 days, we're going to stay much longer days. And now it is time for us to investigate temperature, illuminate, and how we overcome this part, and which place is the best place for us to land and for establishment for lunar base, for human, for lunar ISRU and beyond to go to the Mars. Thank you.
Thank you. And I think this is the end of this session, and I will. Could you please take over the discussion and Q&A sessions?
Будут вопросы к докладчикам, коллеги, сегодня? Questions?
So I guess we can take questions and these questions regarding all the presentation and topics which is presented in this session together. Firstly, may I ask one question to Director Sergey Nikitov about the receivers, SIS receivers. I'm not sure. I mean, whether you have shown that 200 gigahertz receivers for the millimetron, and maybe as far as we know, the millimetron also aiming to observe 350 gigahertz range. So is there any plan for developing such a receivers for space or ground radio astronomy?
Thank you very much for your question. First of all, my name is Valery Koshev. So actually I presented this report, our joint report from our institute, and indeed we have developed 211, 275 band, and now we are thinking about the next band, which is actually very desirable for Event Horizon Telescope, 350. Actually, it's from started from 275 up to 373, which is corresponds to next band of ALMA. So we plan in nearest couple of years to start up this work and try to develop. I think it's possible because I presented also much higher frequency devices which also already can operate. So I believe that it's possible, but it's a different job, different task, and we are going to start this work in the nearest future.
Thank you very much. Thank you. Yeah.
Just colleagues, do you have more questions? No? Probably not. Okay, in this case, let's make a short conclusion, very 2 sentences, only that for me and for, I'm sure for all participants of today's meeting, it was extremely interesting. I learned a lot from today's talks, and this will be very useful for organizing cooperation, at least in 2 fields. One field is millimeter wavelength astronomy, which is probably the future for us now, I mean for Russian astronomy, because in optical astronomy, the last instrument which was built in our country was built half a century ago, 50 years. And we have no technologies, no engineers, no factories to build a new instrument of large size. The only way is to join probably the existing, saying, European Southern Observatory in Chile, together with Europeans to do optical astronomy. But in the field of the millimeter wavelengths, it's extremely interesting, and we hope to organize a special program which will be concentrated around Millimetron project, around SUFA and Russia-Uzbekistan project with large antennas. And we have some experience, as you have seen, in the field of sensors for gigahertz, sub-terahertz frequencies. So it's very interesting subject. And I'm sure we'll cooperate with Korean colleagues very, very effectively. We had to do that. If not, then we were criminals. And second field of interest is, of course, the lunar and moon studies, because moon is everything now. As you have seen, the principal target of Russian space agency, Roscosmos, is the moon. And the same, I would say, about a lot of European projects and US projects, etc. So all the world is very much interested in the moon. I'm not sure, this is my personal point of view, that we need to send a lot of population from Earth to the moon. There is absolutely no sense for that, because we have enough space still up to now, and still a lot of problems on the Earth. So I don't understand why we should send astronauts on the moon if this can be done by machines, by automatic stations, because I'm sure moon is not a good place for life, despite it's very romantic. And the science, if you needed to make space stations for astronomy, it's much easier and much safer to build them in open space, for example, in a Lagrangian point or around the Earth's orbits. While on the moon we have a lot of problems, like dust, like gravity, which is not big, but it exists, like pollution and so on, and day and night changes, so it's very difficult. Well, but in any case, we have to move in the direction of moon sciences, because all the world is doing that, and this is another field where Russia and Korea in astronomy will be cooperating, I'm sure, very, very effectively. We have joint interests, and we have experts and specialists and scientists for these two fields. Okay, so dear colleagues, maybe you will add some words?
No, I'm fine, please.
So tomorrow we'll continue our Korea-Russian meeting, but tomorrow is a completely different subject. As you see in the program, is COVID-19. Only lazy people do not speak about COVID today, so we have to join this big billions of people per company and to discuss this problem for the Earth, for the mankind, and the experts which will be presented tomorrow, they are leading experts of our country and from Korea country. So I'm sure this will be extremely interesting. We start at the same time, at 10, Moscow time. What is, by the way, time difference?
6 hours.
6 hours in Seoul. So in Seoul it's already a little bit late, yeah. And that's all for today. I would recommend everybody behind this door, we have a small, we call this Swedish party, Swedish table, just to relax a little bit and to talk with each other. Thank you very, very much. Thank you all of us.
Thank you very much. Thank you.